Hello, everyone. Thank you very much for joining me. I appreciate your time today. We're going to go through this sort of exciting adventure that I've gone through since 2011, learning as much as possible about wildfires and sort of USACE's role, as well as some of the USGS role and other partners that we've had along the way. To begin, this is not official policy of USACE. This is a lot of experience that I have gained, that our team has gained over the years, and we are rolling a lot of this experience into products moving forward, as well as building on a lot of great work by a lot of other agencies. So to get started, wildfire impacts to infrastructure, planning, modeling, monitoring, and management. This sort of title is what I've been using to try to organize my own thoughts in the different pieces of the puzzle to put together pre-wildfire planning during an event, and then the fires, the floods that come afterwards. So moving in, planning is essentially estimating the project risk due to wildfire in a number of different facets. Once the wildfire is done, that's just the beginning, as all of us in water know, and floods, the flooding is the real danger after a wildfire. I don't say real danger, but it's the unexpected danger that comes along. And one of the things that we don't really have a great accounting now is the scour, incision, the conveyor belt of sediment that moves down the system, lateral erosion that can impact infrastructure, power lines, pipelines, as well as increased flood stage due to increased flows. Planning for all of those at the beginning of a project or when you're reevaluating risk, putting it into your emergency action plan is important to have that planning component built in. In order to plan properly, we need some data in order to feed those planning assumptions, and that's where the monitoring comes into play. Long-term data collection is amazing. We really need to be able to look at an ecosystem, see what it looked like before wildfire, and then go and look at the ecosystem after. The two photos here, this is in Santa Clara Canyon in 2011 before the Lost Conscious wildfire. And then after the Lost Conscious wildfire, it basically had 90% of the watershed burned at medium to high burn severity. Although all the vegetation was stripped off of the watershed, and rilling and gullying began almost immediately. And in this photo from 2014, the rills that you see in those canyons are maybe 60 feet wide, 80 feet wide, and 20 feet deep. There are huge geomorphic features that happened in a very, very short period of time, and it's something that not very many communities are prepared to address. Once we have some good data on the system, the ecosystem before the fire and after, then we can start doing modeling and doing multi-year probabilistic assessments of the recovery path of the wildfire and move forward to make more educated, actionable plans to keep people safe and keep our infrastructure in place. Modeling will help us determine how much incision we're going to see in a channel. This photo is from Peralta Creek, which is in the Lost Conscious burn scar. In one storm, it had 10 feet of incision in this one section, and the channel is probably 50 feet wide. All of this sediment moved into the Rio Grande. It actually caused a plug that had to be removed from the Rio Grande. The next storm that came through actually raised the bed 5 feet and filled in half of that volume of material that came from the upper watershed. Being able to model these types of events and probabilities will help to make infrastructure more resilient, help us estimate how deep pipelines need to be underneath these channels, determine how much of a lee line, how much lateral erosion space we need to preserve to make sure that we aren't putting pipelines or fiber optic lines that are really critical to communities on either side of that drainage to keep them safe. And finally, the management. This image is the delta of Cochiti Reservoir, which happens to be just downstream of the lost conscious burn scar, showing the changes in the delta height from 2011, really from 72 up until 2017. And we saw a dramatic increase in sediment in this reservoir, and this is an Army Corps of Engineers flood control reservoir. As we see the sediments coming into these reservoirs, we now no longer have additional capacity for flood control or for storage for irrigation downstream. So this is the planning, monitoring, modeling, and management, and they all feed each other, and it is its own system in order to properly analyze the risks and making sure that we have a resilient infrastructure and system for people to live and move forward, as well as keep business going. So one of the largest outcomes of the wildfire work that we've been doing in New Mexico is the After Wildfire New Mexico website and brochure. After wildfire began after Lost Conscious, and it's a multi-agency effort. It was written to specifically help communities and people on the ground, this is a boots on the ground effort, work with their community members to prepare for wildfire, help with post-fire treatments and recovery options as far as how to reseed and what areas to watch out for after wildfire, and keep an ongoing, a living document basically to move forward to help communities. As part of this effort, we did a tabletop exercise last year with the goals of improving flood safety preparedness, expanding knowledge of all aspects of wildfire risk, linking all the different agencies that are responsible, from the small local municipal agency that has 3 people that are responsible for trash service in a small rural town, all the way to federal agencies as far as FEMA or the USGS. Then also want to be able to increase visibility, awareness of what technical and programmatic and other resources are available, that it's just really hard to know what tools are available when you're thrown into this environment that is very, very dynamic. It's very fast-paced, and a lot of the features, a lot of the recovery aspects have to be done in a certain order. If you're applying for grants or funding, those need to be fed into a certain order, and there has to be data to back up the claims that you're making for recovery funds. And keeping all of those tools in line can be very challenging. As part of the tabletop, we put together this flow chart of wildfire planning and response. In the initial, and this is customized for New Mexico. A lot of our wildfires start in May, June. We start getting lightning induced fires coming in where we are in the arid southwest, and a lot of our storms are monsoon storms. So that's where the flood risk comes in. So we'll have a fire early in the summer that will be partially contained or contained by the fall or the midsummer when the monsoons come in, and then immediately, a lot of times the monsoons help to put out the fire, but then we get large floods immediately. So this walks through the steps in the basic tabletop. We had 2 hours for this tabletop, so it was a very good prototype to see how the flow worked with the experts that were in the room. It's another nice thing about the work group that we put together. It was all people that had experience with wildfires recently, so they brought their experience to the table as well, and it was very, very helpful to have those experts in the room at all levels of response to feed the discussion. As part of this, I put together demo watersheds so that we could run simulations of different types for the tabletops and have some flexibility moving forward to modify where infrastructure is in the watershed and in the downstream delta area, where the wildfire might come through, where storms could come through, and make it flexible to move forward if we did, as we expand on these training programs. So this was a watershed that I chose partially due to shape and topography that represents some arid southwest. well, it's basically any air lands in the West. That's not true either. The watershed was chosen because it represented western areas. It's actually a watershed in Idaho, but it looked like a lot of the high areas here in New Mexico. I gave the watershed boundary to Keith at the NASA Restore website, which I have some information coming up soon. And he went and they have a server that processes a number of standard products for wildfire response. And it's a joint partnership with NASA and Idaho State University. It's really a very, very useful tool to have, especially in wildfire recovery. All the products that you're going to see in the next few slides came out of that semi-automatic process of delivering these geospatial tools for response. So this shows the terrain and the river systems and some of the infrastructure. As part of the tabletop, we pointed out where water supply was located for Sophia City, what basic services were down in the heart of the community, and then critical access to other resources. We had some ideas of wildfire concerns that we fed into this tabletop, as well as people that they need to be concerned about, and then infrastructure that could be not functioning at full capacity after a wildfire, after a flood. The important part of the tabletop was walking through how someone plans from the beginning of the season to the end of the season. And part of this is understanding the wildfire risk year to year. And there are maps that are produced of wildfire risk every year to know what the forests are looking like and where to put energy. This is very good for bringing real data into the tabletop that you could use moving forward as you're doing analysis. And then we're also looking at the current floodplains. If there are FEMA 100-year floodplains, those are a good starting point to know what the flood risk would be after the wildfire. And there are multipliers depending upon the burn severity in order to expand those floodplains and just to have people be prepared. We induced a lightning strike storm as again part of the tabletop, and then I transposed another burn scar onto this watershed, and the recover team went and ran all of the analysis on the derivative products from the wildfire that I provided. So it was a very, very good tool. This is a summary of the NASA wildfire, NASA Recover Wildfire Data Portal. The list on the left shows all the layers that are automatically generated and provided with the data set. This is expanding regularly. If anyone wants any information, I have the link on this slide, and also we'll post the presentation as well. So that'll be available for anyone to use. The tools that I specifically have been developing, or I've been working with quite a bit, are a rapid response aerial data collection system that we've been partnering with the Civil Air Patrol. We partnered with the New Mexico wing of the Civil Air Patrol, and they happen to have a great, very reliable plane called a GA-8. It's an Australian plane that has a viewport inside for sensor arrays to be installed, and it made it very easy for us to do a lot of experimentation and work with that plane. Automated workflows from this product are 4-band orthoimagery that 4-band orthoimagery and elevation point clouds, as well as derivative products, vegetation health. We're collecting 4-band orthos, so any of the derivative products from there we can use for very rapid analysis. And we have a variety of partners on this program: Civil Air Patrol, Bureau of Land Management, New Mexico Tech, and UNM. as well as USACE SPA and ERDIC, our Engineering Research and Development Center. This is a photo of the camera system that we installed. These are both Nikon single lens reflex cameras. One is RGB and one is near infrared. They collect in parallel, so they are collecting, again, RGB and a near infrared frame as the plane flies along. The mount was made by us here in New Mexico to test on the plane, and it fits that portal. The Civil Air Patrol has 12 of these planes, I believe, in the nation, so we standardized the development to be able to expand other wings for other use in other regions. The UNM GEM Lab, which is the GIS Sciences for Environmental Management Lab at University of Mexico, was instrumental, no pun intended, in developing the camera system and controllers and getting everything to work with the plane. They had a lot of experience with this type of setup, as well as the structure for motion post-processing that we're using to get the data back. We also wanted to make sure that the Civil Air Patrol had access to this aircraft when we weren't using it, so that the sensors were designed to be installed on the floor and they can be left there in between our missions, so the cap can still use the plane for other uses. The flight plans are generated in a laptop with flight control software. We basically provide a shape file, and the software goes and produces the optimum path based on the above ground elevation that you want to fly. And then you can fine tune some details as far as how long you want the flight to be, how long you're going to be in grid, flying, mowing the field. So there's a number of settings that can be set there, as well as adjusting the lens of the camera and when it takes the photos. So there's a lot of flexibility in the tool there to do the flight plan. And then from that laptop, there's a screen for the pilots to use that basically has them follow along a specific flight line, so that we can capture the camera's fire at specific GPS locations. And as long as the pilot gets within 10 feet of one of those GPS locations, 20 feet, it'll fire, and we'll be able to use that data to stitch together an ortho photo. We are looking at upgrading the prototype equipment. The prototype equipment is providing great results. There's a new flight control software with the upgraded GPS that will help quite a bit, and increasing the camera size will, or the frame size, will reduce flight time, because we'll be able to capture more data more quickly. We'll improve the data quality, as we'll have more sensor space. It'll cut the processing time in half, which is really amazing. These are some initial test results from the first flight that we did with the system. We're collecting thousands of overlapping images, and there's a structure for motion software process that stitches all of those photos together. It looks for similar geometric structures between all the photos and makes one large ortho photo of the entire set, which is an amazing tool to have. I think we were flying these about 3-inch ground sample distance, 3 inch to 1 foot, depending upon what we were testing. And this was the initial flight. You can see here just from this image that it, since it's shooting in stereo, it can produce a 3-dimensional image, basically a point cloud of what it was collecting. And this shows trees that were collected, as well as an irrigation ditch. And we have used this technology for flying levees and irrigation ditch during flood season as well, as test results. But we're getting very, very nice results from even the initial tests coming out. And we're working this year to continue fine-tuning the post-processing and get these results even closer. The initial test to validate the equipment and post-processing was done on the Calabasas Arroyo, which is just north of Albuquerque. We flew with the new sensor array with Civil Air Patrol, and had Bohannon Houston, one of our contractors, AEs, develop post-processing methodology using Agisoft PhotoScan, which is a stitching and point cloud generation software, and FME, which is a feature manipulation engine, specifically focusing largely on complex geospatial analysis. And the combination of those two tools allows us to stitch together all of the images, create a large mosaic ortho and near infrared ortho, as well as generate a point cloud from all that data. In FME, we can then take those products and put them through workbenches that will create contours, NDVI products, any of the other derivative engineering products that we want. So the contours we can have exported for AutoCAD or MicroStation, as well as producing 4-band imagery for other more complex analysis. And if we fly the same place over and over again, we can do comparison and contrast between those two data sets. So this is the data we flew with CAP. And we also had LiDAR flown to basically do a sniff test between the industry standard for doing elevation data collection. The test came back pretty good, honestly, for an initial uncalibrated test of this technology. We've incorporated some of the lessons learned from the initial test flight, and we're using those for flights since then. This was a very good check for us to see how close we were, and it was very, very, very good for the rapid response that we can get. Our goal is to use this in a post-flood environment, or if we're expecting some flooding to be coming downstream, to go and fly a levee reach and see if there's any concerns before the releases, or have a baseline to compare the next flight to know where there could be some boiling or some sort of structural integrity issue with the levee system. This is one of the details of results from the Calabasas flight, and again, this was pretty much uncalibrated. We put the sensors in the plane and did a little bit of testing, and then flew this reach, and the resolution on the ground is very good. This is a part of Sandoval County that is all platted, so they have roads throughout the entire watershed mostly, and this I thought was very interesting, that you can see a stock pond that has a breach, and it looks as though the road caused a nick point to start running up and then undercut the stock pond. And this is not a large structure. This isn't basically a rancher went and made a berm to store some water. Same up here, and it's about to come and bypass the second berm. So it'll be interesting to fly again in a couple of years and see if this nick point has actually continued to move itself upstream. And this is a detention basin that is down in Rio Rancho as part of their complex sediment flood control system that they maintain. And again, without really a lot of calibration of the data, there was ground truthing to the data set, but the resolution is very good, and this produces, even at this level, produces some actionable intelligence to move forward. So that was a brief summary of the Civil Air Patrol work. I am looking at using this technology to fly arroyos that receive floods throughout the year, to be able to get high resolution, reach scale, high temporal data, so we can start getting return intervals of sediment concentrations and lateral erosion envelopes on these complex ephemeral systems. Right now, there's no way to quickly go and collect a reach scale, at least here in New Mexico, get a reach scale point cloud after, say, a 1-year return interval storm, and then come back in the same year and perhaps get a 5-year return interval storm and go and fly immediately after that storm, and start making correlations between the storms that caused the 1-year return interval and the 5-year return interval. It's a data set that can help us start to tease out a lot of the smaller events that tend to be the conveyor belt for much of the sediment that moves through our systems. The larger storms are very impressive because you see a lot of the sediment moving, but it's sort of the day-to-day work that the river does to keep the sediment moving downstream. That's the big nut for us to crack. So specifically for wildfire, responding to a number of the wildfires that we've had here in the state, it can be sort of hit or miss. It can be difficult to collect all the data necessary in a very short field expedition, field reconnaissance mission. And this was my effort to try to normalize how to go out and do that data collection. Started out with the reconnaissance kits that are ready to go out and do basic benchmark setting after wildfire and downstream. And these are skills that I learned at the USGS when I worked for them before coming to the Corps, and trying to use as many standardized methods as possible for collecting geometries and quickly evaluating risk in the field and being able to take that data directly back and put it into our models. The surveying kit includes everything that you need for a variety of different types of measurements. The benchmark kit is largely lag bolt based to put into conduits or into trees, so that it doesn't take a large amount of effort, and they're very reliable for long-term monitoring. When the MoBed gauge, which I'm discussing next, is ready, which is the mobile bed discharge gauge, those can be added to the kit inexpensively and installed to collect discharge measurements in post-wildfire upper streams. And then I also included some comfort and safety items so that people can be comfortable. A lot of times, if you're dragging someone out in the field that's not used to being in the field, they don't always have everything that you need. So it's nice to have those as well. This is a list of a variety of the tools that I have included. There's survey gear, drills. I have a little hand level to do some light surveying. I include a couple of game cams that can be installed to capture flows when there's no one around. As part of the pre-reconnaissance analysis, again, the time is so tight to get out of the field and collect all the data that you need to collect. So I started putting together a methodology to identify what infrastructure needs to be seen in the field, just visually, culverts and bridges and water intakes for communities and dams that are downstream of burn scars are all very, very important. But there's other infrastructure that's not on our radar, and that is very challenging for us to get on top of. Pipelines that cross arroyos or rivers. There could be fiber optic cables that go along the channel, and if there's a large flood, that could be ripped out and cut off data and voice communications to communities that are remote. Those things tend to be off our radar, and we don't have easy ways of accounting for them in risk. The regulatory database that the USACE maintains is largely for permitting for modifying waters of the U.S. But it does, when I pulled the data for the Ute wildfire here in New Mexico last year, it showed that there was a fiber optic crossing as well as a natural gas crossing on the Cimarron River downstream of this burn scar. They're probably too far downstream to be impacted, but it's still good to have them on our radar if there are changes to the sediment regime that cause a sediment conveyor belt to move downstream and have extra incision at just the right point could expose a pipeline. And it's at least good to have these on our radar. As part of the report, for the reconnaissance team, we go through and get aerials of the image, and this is largely from Google Earth or from NAPE photography. We do a summary of what's located at that point, do upstream and downstream photos of the bridge or the culvert, as well as measuring the culvert so that we can estimate the capacity. We're also going through, and gaging is very important. Having a data point when building a hydrologic model is so critical. We don't always have staff gauges available. We just don't have the resources all the time. So on this bridge, we painted on the right bank, river right, there is basically a staff gauge that was painted on the wall with 6-inch increments, so that if someone happened to be driving up on this bridge and they saw a big flood and they came out to take a picture of it from either side, there's staff gauges on both sides, it would inadvertently capture our staff gauge and we would be able to estimate a discharge from that event. So it's sort of passive, community-based gauging at this point. We also have the game cams in our field kits, so if there was a place to put the game cam to have its eyes on that staff gauge all the time and collect images every 15 minutes, then we'd actually get a hydrograph from that staff gauge that we could use to assess the risk to this structure. Something else that I'd like to incorporate, and we've talked about this a little bit, is having our teams cross-trained with the BEAR teams, so that when we are in the field doing our infrastructure analysis, if we happen to be near an area that has been burned, to do infiltration testing and add to the burn severity mapping, so we get a much more reliable burn severity map with standardized data that follows the same regime as the BEAR team. And now, this came after Lost Conscious wildfire as well. I was trying to build hydrologic models for this very complex post-wildfire system, and there was no data. We didn't have any discharge data. Every time an event went through, the channel area would change. So, the most fundamental equation in hydrology is Q equals VA. If the area is changing all the time, we can't get to any Qs, and it makes it very, very challenging to calibrate our models. So we happen to have been starting to work with Civil Air Patrol, which was using structure for motion technology, and I'd done a little bit of electronics work. So I had an idea to put stereo cameras onto a low-cost microcontroller and put them in a channel to try to capture the type of geomorphic change that you see in the photo here. This is a photo upstream of Cochiti Lake in Cochiti Canyon in a beautiful upper mountain mixed conifer regime that completely burned out. It had 100% crown burn, and this is probably 10 to 12 feet of incision in the channel that occurred in 1 or 2 storms in a very, very small watershed. I don't have the numbers off the top of my head how big the channel is, or how big the watershed is, but I think it's like 10 square miles. So it's really not a big watershed. And when you look at the size of the cobbles in this column, there was a huge amount of energy coming down the system to not only have this level of incision, but also to move the size of the rocks. And a lot of this is rhyolite. There is a fair amount of pumice in some of these layers, which is very light. Its density is about the same as water, a little bit lower. But the rhyolite has a density that's much higher than water, and it takes a fair amount of energy to move those systems. Anytime we put a pressure transducer in one of these creeks, they just get blown out. And we were starting to have a tally list of how many $1,000 pressure transducers and data loggers went away. The only option that I saw was to have a non-contact gauge that could somehow detect channel elevation, collect the stage and the surface velocities, so we'd have the components that we need to determine discharge. The idea was to have 2 or 3 or 4 cameras hanging on cliffs or trees above the channel that would be looking down on the channel with overlap between all the cameras. The price point of these to make it more reasonable was $500 per gauge. I think we're going to be right up there a little bit less, honestly. The key benefits of the initial prototype, and this is a prototype right now, we're looking at doing field demos this year. Capture a point cloud of the channel after every storm. It's right now I'm having a program to capture the point cloud every day in the middle of the night, basically, and then compare those 2 images. And if there's no changes, then it gets rid of the old one, so we always have the latest. And then if there's a change, then we would have the change in bed form before and after that particular storm that came through and caused that change. We're looking at putting in some new cameras. The development has been going on for 3 or 4 years. Just ran across a new methodology that will actually allow me to do what I originally visioned, which was to basically stop get a picture, the 3D picture of the flow as it's moving down channel. And that wasn't possible a month ago, and I think it's possible now, so I'm really excited to play with it, but it's not quite here yet. We can do video for velocity measurements, and then also capture debris, so we can see how the debris impacts the system. And since it's recording every change, if we get a 6-month event that comes through, we have just captured the geomorphology for a 6-month discharge event at that location in the channel. If a 1-year event comes through, we just captured the geomorphic change, the lateral erosion, the incision. If the resolution of the cameras is high enough, we can get some general cobble size counts to see some of the energy of the system as it's leaving, as the receding limb is leaving behind the sediment, as the energy leaves. We understand that there will be a change in area during the event, but the more detail we can get about the energy of that event, then we can make more assumptions about the bed load that is actually moving and in motion, changing the area for the discharge. So a lot can come out of this as we continue moving forward. Hardware summary, it's using our Arduino. This is all nerdy electronic stuff, so I apologize. Using our Arduino for power management and for triggering, so we trigger by an upstream rain gauge or some sort of movement in the channel. It has a Raspberry Pi to give us more control over the cameras, as well as to serve data. It has a camera multiplexer on it. The Raspberry Pi only has 1 camera port, so this has a multiplexer that can basically get up to 16 cameras on one Raspberry Pi. And my original design was to have it autonomous for 3 months, so I could go as part of a fire response team and put it in the field and then collect data over 3 months and go back and swap out the battery or do something else. The software, the Arduino is all programmed in C. I think there's some other options for Arduinos, but this one is working in C. And then the Raspberry Pi is basically a full Linux computer. So we're running shell scripts, some Python, some PHP, a few other technologies in there. So it's pulling a lot of different technologies together to make this product work as it does. Initial prototype test was taken from a walking bridge in northern New Mexico. Collected multiple stereo image pairs. This is a sample of the pairs that were collected. The Agisoft photoscan software was used to stitch the images together, and then FME was used to derive more products. The location was a very low relief bed. This is really, really flat. There's not a whole lot there. We weren't expecting to get a whole lot from the image, but we did end up getting some reasonable, given the ground sample distance, so the actual resolution on the ground, which, I mean, these are little sticks and twigs and stuff, so the resolution of the imagery was very, very good. We ended up generating contours from that do reflect some of the trends in this particular bed. And this was very, very good validation that the process is working, and now we're moving it into field-based, or basically hardening the gauge so it can survive in the field and continue testing real-world environments. So I blew through 4 different topics that we've been entrenched in for the last couple of years. So wrapping up, the thing that keeps astonishing me, and I keep coming back to this quote that I heard years ago, if I had ever heard of it, it would have been what I had always dreamed of. And for some reason, this just struck me, and it keeps coming back more and more. There's so much work going on in the wildfire environment for planning, get funding sources, how to do post-wildfire remediation upstream, different types of structures to mitigate flow. there's just so much to know that if I would ever heard of this thing that someone just told me about, I would have dreamed to have that. And it's just very, very, very challenging. It's the unknown unknowns, basically. And I think I like this. This was from Dr. Amy Wong from Futurama. So it was good to see that coming from a very technical author. So that wraps up my very rapid tour of a few of the projects that we've been working on. There's lots of partners in the work that we've been doing on these projects, and I know I've missed a few, so I apologize to any agencies that I missed. I'll have to update those as we go. And that is it for me. I do have a couple other, I think we're at time, if I'm not mistaken. So I can wrap up there and we can take questions.
Great, thank you, Stephen. Why don't we, if there's anyone has any questions, please put the question into the chat in Skype, and I will read the question to Stephen. If we don't have questions, maybe there's time if you want to touch on something else.
I buried a couple slides that show some of the upcoming work in HMS. A two-dimensional HMS is coming out for larger sediment transport and to get better refinement of modeling systems, wildfire systems, and high sediment load systems, as well as a new product called MetView that should be released publicly in the next month or two, I think. It's coming out very, very soon. But I do have a few slides on that if there's no questions.
Great. I think we'll probably have time for that. There's one question that came in. Who funds the post-fire or post-flood rapid assessment Civil Air Patrol flights when they are needed?
We have two different sources of funding for those. There's a Rio Grande collaborator program that we're using for a considerable amount of work on the Rio Grande. It's there are several endangered species on the Rio Grande, and it's a very complex dynamic system. So that funding has been used for the CAP flights on the Middle Rio Grande, and they're not that expensive. We're basically paying for flight time, and we're only using it for emergency operations, so that there isn't a large amount of funds that are going towards the flight time. We also have received some funding from ERDIC, our Research and Development Center, for collecting data for sediment model validation and post-wildfire geomorphic dynamic analysis.
Great, thank you. Another question came in. What steps do you think will be needed to protect stationary cameras, for example, from theft or firearms?
Abundance and redundancy. Being in New Mexico, I grew up in California. I was born in Walnut Creek and grew up in the San Francisco Bay Area. Coming to New Mexico is a little bit different. Anything that's in a remote area becomes a target to shoot at. So camouflage is one of the best deterrents that we can have. And also perhaps putting a sign on it that says that it's protecting whoever happens to stumble across it. Let them know that it's protecting them from flooding, to try to have people leave it alone. But there isn't a good way to ensure that they will be safe. Since these will be high up in trees or on cliffs, they are a little bit less susceptible to theft. And if they're not sparkly, hopefully they won't be easy to spot to shoot at. So those are my two biggest hopes, that they just won't be accessible or visible.
Great, thank you. I don't see any other questions. If people do have questions, just go ahead and put your question into the chat. But we do have a couple minutes. If you want to touch on some of the HMS upcoming features, that'd be fine.
Okay, sounds good. I can jump in for questions if any come up as well. Let's see what's going on here. So this is a new product that's been in development for 3 or 4 years, and it's been refined, called MetView. It's produced by our hydrologic engineering center in Davis, California, and it has been amazingly helpful for processing gridded precipitation data and doing ground truthing from tipping bucket or precipitation rain gauges. So you can bring in NextRad grids, or however you happen to get your precipitation grids, and then if you lay a series of subbasins over that grid, it will automatically generate storm totals for the subbasins and volumes, which is amazingly handy. It can export hydrographs of those subbasins, so you can see how that storm was impacting each of the subbasins and look for some trends. But it'll also ground truth if you have rain gauges. So if there's a local rain gauge, or you're using some weather underground data in a remote area, you can use that to go and improve the quality of the NextRad. It is a gridded data tool, and it's brand new, so I haven't really dug under the hood as much as I would like to, but it can basically pull in a lot of different grids, and it works on tins. So once it brings in the grids, it converts it to a tin, and then it does the manipulation with the triangulated network, which is more efficient than a lot of the grids. And then it can piece together, it can basically go and export new grids of various sizes or tins to be used in a variety of settings. So it's very, very handy. I'm really looking forward to digging into it a lot more. It will also do design storms and HMR, whichever HMR version you happen to be using, built in. So it can automate a lot of risk analysis for you, which can be more complicated than it needs to be. So I'm looking forward to playing with this as well. This is a brand new product. Last I heard, it was coming soon. Let me put it that way. I'm hoping before we get into monsoon season, so I can distribute it to a few more people. This is definitely going to be a very, very good program to move forward for a lot of precipitation analysis. And I'm not sure how touchy it is in California. Here, since we have very few radar stations and lots of topography, there's lots of radar shadows in New Mexico, and areas where there's just drift between the ground truthing and the radar, and we don't have ground truthing everywhere. So it's very challenging to put together any hydrology models, because there's if the precip is off, everything else is completely off. You can have a numeric model that perfectly matches the physical system, and if the precipitation that you're feeding it to match the downstream gauge that you're calibrating to is off by 15 or 20%, then until you get into the higher, more extreme storms, there's going to be more error as far as sediment transport, lateral erosion, a lot of the sediment movement downstream. So input precip is very, very, very important to me, and I'm glad that this tool is coming out to help us refine that, or at least know what the error is in larger scale precipitation analysis. And this is HMS 2D. There are a couple other versions of HMS. I believe there's a new version of HMS that came out recently, and then there's another update to that that's coming out a little bit later this year. And then the team is getting to finalize the HMS 2D analysis, or HMS 2D component, which will have there's a number of improvements, and I'm not the developer in this. I haven't played with it, but I wanted to at least show some of the slides and what they've been working with. I'm really looking forward to playing with this product as well, to see how it can improve our sediment analysis and a lot of the post-wildfire sediment transport issues that we have. This is let's see if this is going to work. This was a video, but I don't think it's going to be happy playing it. So maybe I can put a link to this video up if anybody's interested in watching it later. And this was a video too. And normally in the regular PowerPoint, it showed a play control. Huh, that's weird. Anyway, if you can squint your eyes and visualize all of the drainage networks here turning from blue to red and back to blue as sediment moved through the system in 2D, that's what you'd have for this slide. This slide plays a multi-year analysis of the system and shows the change in bed elevation, a change in velocity, change in, it basically is showing all of the variation and changes of the system over an extended run simulation. So we're looking at 2 years or 3 years or 4 years so that we can start really seeing how vegetation recovery in a watershed. We can run Monte Carlo simulations on the precipitation that will be coming into the system over multiple years, on the vegetation recovery, any ecotone shift, and run a variety of long-term simulations to see what the best remediation efforts long-term may be. And I think that one does, yeah. So that was the last of these slides for me.
Great, thank you very much, Stephen. And you had 2 videos that you had linked earlier in the chat. So I'm pasting that into the chat right now so that people that want to see those flood videos, they can follow those links and do so. Thank you very much, everyone. I don't see any more questions, so I want to be respectful of everyone's time. Thank you very much for attending. Please stay tuned for future topics coming up very soon.